need the interaction. But so in the last decade, we have like worked on the tracking, hand reconstruction, and many wonderful products using this. And my question is, what can we do more with our hands? From this data set, which we collected several years ago, we use hands intensively to interact with our surroundings. And currently, the humanoid robotics are very popular. And our goal for the humanoid robot is to enable it to achieve the general manipulation skills like our humans. But what's our current situation of this direction? So the first is like very popular work from Google is a series, and we can see the pick the object as required by the user, like move banana to some. Yes, it is very good, but how far are we away from some very high? And if we want to do some more complex tasks like this, I think it's more challenging. And what if we perform like tasks like using the tools? I think it's a very challenge. And in current research, like for example, people usually high-level planning with large language models, and also other presenters today, they have introduced like internet scale data to actually to understand how we human perform and how we human manipulate objects. Also, we can reasoning about how to perform a task. We can do several subtasks. But the question is, how can we achieve low-level planning to control the subtle movement of the complex, for example, and the effectors like humans? So this is my talk today. So for answer these questions, many researchers has attempted using our human the knowledge or priors from a human. For example, in this work, they built a retargeting network to retard the human pose to the robotic pose. Also, they use the reconstruct hand as a reward in the RL learning. Also, very classical reinforced learning methods using the human demonstrations. Also, like we can also see in robotics, people also use content map to gather a natural grasp pose. So we can see in the community, also in the robotic community, people use intensively about using this hand object in understanding knowledge for robotics. So for today, the topic is I will go from the reconstruction to the generation, like hand generation, and also we go through from the CV community to robotic community, how to start from the generative hand to the robotics that can interact with the physical world. So one key, I think later I will show some, maybe answer the question, one of your reason just now, how to capture the physical contact or the physical data that exists in the interaction of the robotics and the physical world. So the first problem is we are very familiar in the hand reconstruction community. Is like given a video of the input sequence, we want to reconstruct a 3D hand mesh. So for this problem, I think many people have worked on this topic. In this setting, like in existing work, they use the hand as the prior for the pose and estimate the object from multi-views. But for this work, we can see under the occlusion areas, we cannot get to observation. One way is to use the SDS laws as mentioned just now. They can actually how to say recover the occlusion areas, but it will also lead to some degradation in the thin area. So in this method, we use another solution. Here is our reconstructed mesh. So our solution is that we use some the physical contact and also the object, the silhouette of the object. For the first part, we think like the silhouette of the object can constrain the overall shape. So we use some impeding network to recover the occluded area to make it perfect silhouette or the mask. In the next part, we use the contact parallel because if when we hold the object, we know we can use the hand estimation like to know where our hand is, and because we are in contact with objects, so we got the parallel. So the surface is in the contact area of our hand, right? So use this information. I know where my hand is, and I use this information to recover the surface of the object. That's the major contribution of this work. And we can see with this like a model completion task is we can get some global shape and use constraints like the local constraint from the physical contact, and we can get a better global shape. So this is the first work about how we can use the contact from the interaction to recover a better shape. And for this better shape, we can use the reconstructed shape for some manipulation task. On the other hand, I also work on the 3D hand generation. So in this problem, it's like given an object, we want to generate multiple grasp poses. So I think for this method, like many people have worked on this, and it's quite a popular question, also a very popular problem. And in this, in many of the literature, they treat this problem as a direct mapping from the object to the hand pose space, and also the hand pose space of the distribution. But I think it is highly nonlinear because the object is in the 3D point space is X, Y, Z, right? And while the hand pose is in its rotation space. So the mapping is quite a highly nonlinear mapping problem. So in this, in our work, we wanted to break this question into two sub-problems. First, we generate the contact map, and from the contact, we generate the hand pose. Why it works? And we think because this space is kind of a classification problem. If we just classify which point is in the contact or not, whether it's in the contact area or not. So the space of the input and output are perfectly aligned, just some classification or the generation of the content map is quite easy instead of learning the the mapping in the pose space. So once we get to the content map, we assume if we have the content map, our hand is fully constrained by the content map, then we can use some one-to-one mapping network to solve this problem, which is quite often in hand reconstruction. For example, if we treat this as a point cloud, and this is like the partial point cloud, and this is the final pose we reconstruct from the partial point cloud. So with this insight, we just decompose our problem into two stages. First, generate the content map, and then get the grasp pose. One good thing about generating content map is that we can use this information for some partial refinement for the final pose. As we can see, if we get the content and we can do some partial optimization instead of a global optimization, because we know whether our pose is in consistency with the generated content map. And then if it's not in consistency, we only refine poses causing the inconsistency instead of the global pose. So we can see like with this simple strategy, we can get very a large improvement in the simulation. Like this is the displacement in the simulation environment, and this is the penetration. We can get much more data close to the less displacement and less penetration. So this is some result. I just want to emphasize that this is the direct mapping from the input to the pose space, and this is the in the two stage. First the contact map and the second pose. Just a simple factorization. We can input the success rate. This is the success rate in the simulation to about 20%. So some interesting visualization, like we generate one content map and the other content map, and then we interpret in its latent space and get the final grasp poses. So in the following work, we also replace the contact VE. Just now we use the contact VE as the generative model, and we use the incorporate the powerful diffusion network into the contact VE network. So this is we use the diffusion network in the latent space, and we can see this is the contact VE structure, and use this contact latent in the latent contact diffusion. We improve about 10% in the success rate. So just some latest work. So here we have get the target pose for object like this. For example, for a thesis, we get a target pose. But how can we generate a collision-free path to this pose? It seems like for many objects, it's quite easy. For example, for this microphone, I just get the target pose, and I start from some here, like the open pose, some default pose, and we just interpret from this to here. But for many objects like this, it's not easy. You can get penetration easily, and you just tip down the object. So this problem, we want to find a optimization method to plan a path from the some default pose to this target pose. Why we want to do this? One way is like we want to do some path planning for robotics, and also when we want to do some diffusion method to do the 4D motion generator, we find out, oh well, there's no data available. Okay, there's no large data available, large scale data. We may have some data set of 50 objects, maybe 100. I think the most the largest data set I know is about 50 object of 100 data sets. But how can we deal with more complex scenarios in your daily life? So we want to first use some motion planner or optimization method to create a data set for some diffusion-based method. So to begin with, to solve this problem, we find no method for this problem. We have some sample-based method for the robotic arm. Also, this is some gradient-based optimization for robotic arm. Also, some generative model. But when we use generative model, the quality is doubtful, and because the also data is also limited. So it's like a chicken and egg problem. So in this problem, in this method, we want to solve this problem. The problem is that given a target pose, we have and start pose, we want to find some configuration for all the poses in between. For example, if we discretize the trajectory into n step, we want to solve the problem of n multiply 51 if we use a manual pose. So the parameter space of this optimization problem is quite large, and also, we don't want to use this formulation because solving this problem is like you solve maybe thousands of parameters that are independent of each other. It's quite difficult to solve this problem. So instead, we use some method like I treat this the joint of a hand as an agent. So each agent need to go start from a start pose to the final pose, and just some agents like they move fast, and some agent move slower. So the different speed form the different pose. So my solution for this problem is that why not we use some function to control the speed of each agent, each angle, instead of this formulation. So then we use some function like this. Use this function, we have the function to speed, like to speed or to delay the tempo, the movement. For example, if we make it the hand to move slower, all the agent, all the joint move slower, like they keep this pose and they faster at this stage, they get some good position to go through the hole. But if we move quick and we make collide with the object. So instead of optimizing in the original space, we find a parametric function to mapping the time to another space so that we can control the speed. So this is some insight of this work, and it works. So we can get some pose that can go through these holes to get to reach the target pose, but also we also have problem of unnatural poses. So because we treat these agents, all joints as independently. So what to do is, how do we solve this problem? We just then use some autoencoder we call neural poser to learn a lower embedding of our pose space. So and learn this network by a large hand pose data set. Then we, instead of optimizing in the pose space, just now we remember, just now we optimize in the manual joint pose space. Currently, we optimize in the latent space of the hand pose. Now we reduce the problem from this, the number of parameters to these parameters. So it's quite from in this dimension, I think we use 10 or 7 dimension. So we reduce thousands of parameter space to tens or dozens of parameters. And here is our optimization method. Instead of optimizing in the original pose space, we optimizing in the parameter space, the temporal parameter space control the speed of the joint, the movement of the speed. And also we optimize in the latent space. We use the encoder to transfer the pose space into the latent space and optimize in this space. And here is the gradient, like we get the trajectory and calculate the gradient and update the parameters. So that's our solution. Let's have some comparison with this neural poser. We can rectify the unnatural poses and compare to the baseline list one. You can get penetration easily. If in a simulator, you will just make the scissors fall. And for sample-based and optimization-based method, they are initialized with the baseline, and you can see the jittering of this method, sample-based, because it's used some RT path planning. And this one, because the initialization is like this, so it is very hard for it to get skipped, get over the local minimum of this initialization. So some comparison with the existing work, I will emphasize the improvement in the success rate and the the time or the speed of optimization. So here are some results in the simulation. So what I think the method is, the value of the method is like we can get a high quality data set that can operate in the simulation. So here's some video example without some component of our method. You cannot grab the object in the simulation. So this is the value of our data. So here we generate like about a 1 million motion sequence with like 8,000 objects from the Dexter GraspNet or OBMan and the other existing data sets. So with this, we can now maybe using some body motion diffusion generator or generative method to get more grasp pose that can operate in the simulator in the physical world. Some just to show some potentials. So until now we have we all talk about the grasp, but in our daily lives it's not just a grasp, right? We do some very complex skill manipulation, like screw a bottle, right, and slide something and hand over object. So but for this manipulation task, it's so difficult for a reinforcement learning method to start. Even it cannot get trained because, for example, I have two hands. I first grab the object and unscrew it. So the complex of this high dimensional space making the algorithm hard to find some find some reward. It's too hard for them to accidentally find a solution and update the network. So our method is like in this part, my research is about how can we use like more priors from our humans to help the learning of the manipulation skills. So in this method, in this series of work, we can see like for the pre-train, many people in robotics use like the large language model, for example, the MVP using MAE, and some contrastive learning. R3M uses contrastive learning for some representation in the vision space or maybe in the language space. But as discussed just now, in manipulation or in robotics, more about the context. The context is very important for a successful manipulation. For example, if I want to grasp an object and pull it down, the force change constantly. How do you infer the change of force from vision? It's quite hard, right? So my question is like, how can we leverage this information from human? Yes, and in robotics, we may have some tactile sensors to capture this interaction information. For example, the very popular gel set, it can capture very, very precise force, but it is too bulky to attach to human hand. And also, we have some very flexible gloves we can wear, but it's from nature. It's a nature paper, so it's very hard to make this graph. What can I do? I'm just a researcher, a young researcher. I cannot make such a delicate and sophisticated gloves. So what I do? So if I cannot get this complex tactile, I can maybe use some cheap solution, right? I bought some sensors, tactile sensors from the Alipay or Alibaba, and it's cost about $2, and attached to a glove, knitted glove, and also outer glove to prevent the worn out of these tactile sensors. And collect the manipulation data from the HoloLens. We have the vision, the point cloud, also the tactile sensors. And here are some example. And this is the tactile sensors, the signals when we perform this task. So with this data, we use some follow some pre-training network. So the detail of the structure I just skip is just like some MAE network to reconstruct the mask input using this network, and we use this the render embedding and into the AI framework, some existing work. And what we want to investigate is, can they help the perform this task this is our result. It's not from the existing work. It's very hard to train this work if we lost the human, the visual and the tactile sensors, the pre-trained network. So this is our result of the performing this very complex task. So how can we realize it? And so if we, here is some output like or the experimental result. So here is the vision and the tactile sensor without pre-train, without our data pre-train, human manipulation. And that is the pre-train, the vision and the tactile pre-train. And we boost the, at first, if without pre-train, for example, the bottle turning task, we cannot even make it start to train. And after the pre-train, it boosts the performance to almost 90% of a success rate. So here's some like the ablation study of the network. I just skip it. And one thing I want to emphasize is the attention map, because we use some transformer. We can see like this one is no tactile sensor, and this is a tactile sensor for the attention. If we have some contact in the contact, like the tactile sensor, if it's in contact, the attention map mainly attend on the related hand-related area of this the finger, right? So if we compare this with this, without a tactile sensor, the attention map is more scatters more broadly. It's not focused on the gesture of the hand. So here's some comparison. So we want to see if we train or pre-train the vision and the tactile sensor simultaneously, we can achieve very robust results on different tasks. And if we use a tactile sensor only, yes, it can perform very well because we place the hand near the object. And if we use the vision, yeah, some tasks are okay, but some tasks cannot start the training. So here's just some example. And following this work, we have more work to come. And the other question is, any other way to incorporate the tactile sensor? We usually pre-train network. Can we incorporate it in other ways? For example, if because in this setting, we usually synchronize or pairwise visual and tactile sensor. What if we just have a tactile sensor or just only the visual data, because we have larger scale visual data, right? But we may don't have the tactile sensor or tactile signal aligned with these images, right? So here we just explore the other way. We use our LSTM to learn the tactile pair and incorporate it as the in the reward, just the loss of the LSTM as the reward. And we can see some interesting results. It also can achieve similar performance with the joint pre-train. So this is some interesting findings. And this data, with this structure, you don't need the pairwise data. And the other question is, can this visual tactile pre-training work for the manual manipulation, for example, by grasp and turning the bottle? We apply the framework to this task directly, and we find out it can work to some extent, but the success rate is not high enough. It's only 40% for seen object and 30% for unseen. And then we want to investigate how can we boost the performance for this this very complex, like the coordination between the two hands. So here we use last investor action. This is quite common. Like we just now we mentioned other presenters introduced many motion data, right? So we use this network to predict the future actions, and also we predict the pose of the object. Some interesting finding, and here is the we share the tactile, and we add more information about the object. It boosts the success rate to a little bit, and the action also a little bit. But if we combine them together, here is the result. So the action, the sensing of the robotic hand itself, and the environment, the combination can make a huge boost in the performance. So maybe some results like in the, maybe I skip this one. Yeah, my time is, okay. And my time is up, and now I just very briefly introduce my work about just we propose some local representation for the grasp, because why we do this job, because if we use a point net feature, we can hardly train a network, grasp network in IR because the sparse reward, right? But if we use our proposed feature, we can boost the performance from here to about 90%. And some quick results, we train only on 40 objects, and we can get about 90 success rate on unseen, 5,000 unseen objects. We can get about 90%. And some concurrent work, they train on 3,000, and they test on this 2,000, and they achieve about 75%. So here is my work, and as my time is due, so here's some summary of my work is from hand reconstruction, and and generation and manipulation. I have watched all this problem like with the colored ones, but there are still many unexplored questions, unexplored problem in this community of waiting for us to explore. And thank you for listening. Thank you.